Solving optimization problems. Yes, these are going to be word problems. And if you think about it, every example we do in this course should all, and have been all, word problems. But we have to be able to translate what it's telling us in English to math. Because we can do the math. It's just like, can we read it? And that's what this whole thing's about. There are 5 steps that we're going to deal with. What do you think the first step is?
No.
Yeah. Read the problem. Understand what it is giving you, and wanting. We have to know what it says, because simply by reading the words in the equation, we know what formula we have to use. For example, if it says, I want to know what the length of the perimeters of this rectangle is to maximize. If I want to put something border around this here, and I want to maximize it, make it the most efficient, what size borders do I need? Since I'm dealing with parameters, what formula do I use? That's area. What's the formula for perimeter? You said it.
Yes.
Yeah. So a perimeter is twice the length plus twice the width. The width, length. So again, it's given to you. The formula is given to you in the question. You just have to figure out what formula to use. If I want to know the area of a rectangle, length times width. If I want to know the volume, base, height, and width. If I want to know the circumference of a circle,
Pi r squared.
it's pi r squared. What is the area of a circle, of a sphere, of a volume of a sphere? Pi r cubed. And then I'll show you later on, but those two equations, 2 pi r versus pi r squared, think about it. 2 pi r versus pi r squared. What is this one? Is that the area or the circumference?
Oh.
It's the area. And this one is the circumference of the circle. But look how they're related. Do you see any mathematical operation that goes from one to the other? What? If we take the derivative of this one, what do we get? So it's the same as acceleration and velocity. So that's how areas and circumferences, or volumes and it's not the area, it's the skin, there's a shell. Surface area, yes. The skin, but yeah, it's the outer shell of the object, of the sphere. So yeah, there's always these kind of relationships that we have to know. So first off, read the problem until you understand it. If you have to, I always do, draw a picture. and label what you have. And label what you can. Define the variables used. Base, width, height. Those are all variables because they change, especially in optimization problems. We've looked at the variables. It's giving us all this stuff. It says the width is, the length is, the height is, but now we have to define what equation is being used here. Will you only have one equation? Or no, you'll usually have multiple ones. Because what you have to do, what's not written here is once you have those two, you also have to find the relationship between the variables. Once you have all that stuff, plug them all in there, solve. Work out the problem. And then CYA. What does CYA mean? Yes. Check your answers. Make sure it's valid. Make sure it's legitimate, what it's supposed to be. Yeah, it sounds easy. Let's see how that works. And there are a whole bunch of types. And if we have time, we'll also cover what are called initial condition problems. Got this? All right, let's look at the first example. Example 1. And open top box is to be made by cutting congruent squares from the corners of a 12-inch by 12-inch sheet of tin. And bending up the sides to form a box. So the question here is, how large should the square cut from the corners be to make the box as much as possible. Oh, to make the box hold as much as possible. We have to read the question till we understand what it's asking. Because if you understand what it's asking, then you can draw a picture. So what's our picture gonna look like? Well, first off, we have a sheet of tin that's 12 inches by 12 inches. Right? What do we have to do with this sheet of tin? We have to, a box is to be made by cutting congruent squares from the corners. What does congruent mean? Same. So we want the same size to be cut at each corner. Because then we could bend up the sides. Trying to make a box. As I said, it's an open top box. So what do we have to look for? Are we gonna look for perimeters, areas, volumes, circumferences, or what? We have area, surface area, volume, what else do we have? Think about it, what is it asking? How large should this square be cut to make it hold as much as possible? Make this box hold as much as possible. So what is the stuff inside a box gonna be? What formula do we have there? What is that? I know what you, we have the height, we have the length, and we have the width. What's that called? That's what you were trying to say. It's a V, excellent, very good. Yes, that's exactly right. Because we have 3 dimensions, it's a volume. What is area? The area is the stuff on top of it. How much would be, it's only 2 dimensions. It's base times width. So it can't be area. The area around it is the length around it is the perimeter. We don't want that. We want the volume. So we're getting closer. We just have to figure out now what is W, what is L, and what is H. And that comes from this. Do we know how much we're gonna cut from each corner? No, so what do we label that as? X. And both of these, since they're equal, if they're squares, they both have to have the same size. So we'll do all of these. So if you look at this, which one of these variables can be defined by X? The height. Because that's how far, that's how much we're gonna fold up. So we have one of these is defined as X. That's the height. Now we gotta figure out the width and the length. What formulas do we use there? Looking at this picture, can you tell me, let's call this the length and this the width. What formula do we use for the length?
X minus, X
That-
2x.
12 minus 2x. Because this is 12 inches originally. We cut out X inches on both sides. So it's 12 minus 2x. Because it's a square, it's the same thing for the other side. So it's 12 minus 2x. So our volume is the height times 12 minus 2x squared. Why is it squared? Yeah, because it's a square and both, so the length and the width both have to have the same values. We have a formula. What do we have a domain? What is my domain of x's I can use? Or how'd you get that?
Because you're gonna need the number to kind of form number one.
No. Well, good thought, but no. I see where you're going with that, but no. Look at this equation we have here. Can x be 0? No, because if x is 0, our volume is 0. Doesn't hold anything. Can x be 10? 10 inches? Why not? Well, well, let's see. It could be 10 inches because remember, we have 12 inches to deal with. If I cut off 1 inch from both sides, then it's 10 inches long. Well, the x would be 1 at that point. It'd be 1 inch here, 1 inch here. So it'd be still 10 inches in the middle. My domain, you're right. I'm looking at what size can I cut out of there? Yeah,
It could be less than.
well, if I cut 12 inches, if this was, no, you were close. You said it there. No, you said it there. What did you say? Yes. Because you have two corners. They have to be the same width, right? If this is 12 inches, if that's 12 inches, what's the most I can cut from this corner and this corner? 6. Because this half and this half, I can't go any further than 6 inches. But yeah, so that's still, in other words, my domain is x has got to be between 0 and 6. Even though you're right, at 0, it's a flat sheet of paper or a sheet of tin. At 6, it's just a folded piece of, it'll hold nothing. But it's got to be we know it's got to be something between there. 2. Yeah, you have to figure it out first. How'd you get 2? It just sounds nice.
No, I mean, either way has to be a positive number, and not a positive number, of even number. So you cannot take out 3. I feel like 2 is a good number, because you want to have as much as possible. And because you just can have 2.
I'm glad we're not designing an airplane or a rocket. Let's try, let's try this. Okay, go fly it. Oops, I guess we need longer wings. So we know that our X values, our final answers have to be between 0 and 6. That's just our domain. But now, how do we use this equation to find our potential maximum? Do we know any mathematical operation that gives us, that tells us what to do here? So it's the only thing we've really been dealing with this semester so far. Okay, first off, let's go ahead and fix all these. Let's do this one first. So we have 12 minus 2x squared, which is 12 minus 2x times 12 minus 2x. 12 times 12 is positive times negative is negative. 2 times 12 is x. Same thing here, negative 24x. Negative and negative makes it a positive 4x squared. So we have 144 minus 48x plus 4x squared. And then we have to multiply this one. So the volume is going to be 4x cubed minus 48x squared plus 144x. And remember, we're looking for the maximum. Is there any mathematical operation that we've been dealing with forever that we can use to do here? The derivative. Because we want to know if we take the derivative, for example, how do we find the vertex of a function? Take the function, take the first derivative, and set it equal to 0. Remember, the first derivative is a slope. Where is the slope 0? That's at the vertices. So now we'll know what the highest and lowest points are of our curve. That's what we're doing here. So if we take the first derivative, what do we get?
Squared minus
96.
x plus 141.
Yep. Now we got to take that, set it equal to 0. Do they have anything in common? Yeah, they each have a factor of 12. So x squared 7, no, it's 8 plus 12. Now we can factor this one. So we get x and x. What signs go in there? Yeah, since the second sign's a plus, that means both signs are the same. They're both the first one, so they're both minuses. What times what is 12? When you add them, you get 8. Yeah, 6 and 2. Solving for these, set them equal to 0, x equals what? So these are the size of the corners that we can cut. That'll give us the maximum volume. It's just constant. It doesn't affect anything.
Oh,
So how do we test to see which one's correct? Which one gives us the highest average value? Plug them both up into this one. If we plug in 6, let's see what happens. So we have V of 6 and then V of 2. But because our domain is from 0 to 6, we also have to look at 0. You have to look at the domain, the bounds of your domain, A and B, and then have we seen this kind of equation before? Yes. Whenever we look at functions to look for the maximum minimum, we take the endpoints of our domain and then any point we have in the middle. And if we plug them in there, what do we get? So let's use this equation here. If x is 6, 2 times 6 is what? 12 minus 12? So that gives me 0. When x is 0, 0 times anything is 0. Now how about 2? 2 times 2 is 4. 12 minus 4 is 8. 8 squared is 64. 64 times 2. Hey, we have a clear winner. We have a clear winner that the walls, if the corners we cut are 2 inches by 2 inches, then our volume is 128 cubic inches total. So 2-inch cuts will give us 128 cubic inches of volume. Yeah, those we have here. Yeah, it goes more than I thought. Any questions about that? You see the process we have to go through. Does the picture help? Yeah, it should, because it gives us a better understanding of what we have to do. And it also helped us understand what our domain is. Because if we have to cut equal sides on both of them, if x is 0, then we just have a flat sheet of 10. If it's 0, what's the volume of a flat sheet? If it's 0, it's 0, because there's no volume, no height. Now, both of these sides have to be the same. Can we cut 10 inches? No, because if this one's 10 inches, this one can't be 10 inches. So we know that we can only go halfway through. The way we did that, take our equation, set it equal to 0. These two values here, once we factor take those and set them equal to 0, and that'll tell us our maximum and minimum numbers. X equals 0, check. 12 minus 2x. Set that equals 0. 12 equals 2x, divide by 2, x equals 6. That's how you get your domain. Now, any of our answers that we come up have to be inside those. Let's look at another example. Example 2. You were asked to design a 1-liter can shaped like a right circular cylinder what dimensions will use the least material? Well, let's draw a picture. What are we looking at? A cylinder, so it's like a Coke can. And it's a right circular cylinder. What does that mean? A right circular cylinder. No. It means it has to have a 90-degree angle. I know, when you first read it, it sounds weird. Why do they say has to be a corner, a perfect corner, or so that they use that it's a right circular cylinder because it creates a right angle. So inside here, this angle is a 90-degree angle. And this angle up here is a 90-degree angle. So if you look at the can from the side, it's a square. Or a rectangle, I should say. That's what it's telling us. The corners of the can have to be 90-degree angles. So what formula do we have? So what's the formula we would use for a circular cylinder? And we want to be able to put the most inside there. Well, yeah, you're right, though. We could use width, base, and height. So we have the width, the height, and the base also is in there because it's circular. So what is it going to be, an area or volume or what?
Oh, no,
You're defining the surface area, but what's inside there, you're trying to fill, because it says it has to be a 1-liter can. So it's a volume. So the volume has to equal 1 liter. And this is also where it gets complicated. What's the formula for the volume of a right cylinder can? It's actually 2 equations. Very good. The base is an area of a circle. What's the formula for area of a circle? Pi r squared. If you think about it, volume is what? It's the base. The base is the area of this circle times the height. So it's going to be area times height equals 1 liter. You're asked to design a 1 liter can shaped like a right cylinder. All right, so we have a top and we have a bottom. So we'll have two of those, but then that won't deal with the volume. You're looking for surface area. Right now, we're looking for volume. It's this area times the height. So it's it's pi r squared height. What do we do now? What is the unit over here? Since it's a volume, it's cubic, right? This is 1 liter. Are they the same type of units? No. So we have to make this side into a cubic unit. How do we do that? 1 liter is made up of what? So in other words, what we're looking for here is, can we break this up into 3 equal numbers? Because it has to be a cube that equals how familiar is everybody with metric systems? Yeah. What's that? Well, yeah, it's going to be because you're putting stuff inside there, so it'll be physical. Ten times 10 times 10 equals 1,000.
Oh.
The beautiful thing is this, in our SAE system, our English measurement system, we cannot go from liters is liquid. We cannot go from liquid to solid measurement. You can in metric system. Think about this. Think about when you go to a hospital, a doctor, and they give you a shot. What do they measure it in when they give you a shot? cc's, cubic centimeters. Centimeter is a distance, but the stuff they put in the shots is a liquid. So now you have a solid and a liquid being compared. That's the beauty of metric system. So we needed something that could break down into 3 pieces that equal 1 liter, and that's the cubic centimeter. You can't use meters because that'd be 1 meter times 1 meter times 1 meter. That's just too big. That's 3 foot by 3 foot by 3 foot. That's monster. So the conversion is this: 1 liter equals 1,000 centimeters cubed. So what we have here is we have pi r squared h equals 1,000 cubic centimeters. Now what do we do? You're asked to design a 1 liter shaped can, the right circles. What are the what dimensions use the least material? So we know this, the size and everything. But what material do we need to use? You said it earlier. We have material on the top, we have material on the bottom, and we have material all the way around. So we have 2 of these circles. So we have 2 circles. So 2 areas, which is 2 pi r squares. So that's the top and bottom. What about the length on the outside, the shell of the can? So this defines our 2 top and bottoms. Now we have 1 wall that's in the shape of a circle. So, but it's not a circle like this, because it's just the outside, which is the circumference. What's the formula for circumference? Two pi r. So that's the length around the circle. And then we have to go up the can times h. So the surface area is the 2 circles. So we have 2 pi r squared 8, or 2 pi r squared plus 2 pi RH. So there's a top and bottom, and this is the wall. That's the surface area. What problem do we have now? Too many variables. We have too many variables. We have R and H. Ooh, no, why not? Because we're looking at exponents. R plus R, does that equal R squared? No, it's gotta be multiplied. You can only add and subtract if it's the same terms, common terms. So if you add R squared to R, you don't get R cubed, you get R squared plus R. What's that? Mm-mm. So obviously the radius is gonna be an important factor, because that tells us how big the can is. What about H? Can we find a value for H that deals in terms of R?
Oh, replace that equation with 1,070.
Yeah, we saw for H. So we know that pi r squared H is equal to 1,000. Solving for H, we get 1,000 over pi r squared. Remember us in the notes earlier, we had to find the relationship between the variables. This is the relationship between the variables, between H and R. So we have the surface area, and we have the value for H. What do we do now? So the area now becomes 2 pi r squared plus two pi r. What is h? 1000 over pi r squared. Now we have one equation with only one variable, r. So if we simplify this, we have two pi r squared. The r's cancel. So we have 2 times 1000, which is 2000 over, oh, and the pi's cancel. So we have 2000 over r. Get these guys out of here before midnight. So we have our formula for our area of the can. We want to know least material. So what do we got to do with this? Maximum minima? How to find maximum minima we got to do first? You have to find where the derivative equals 0. So we got to take the derivative of this function. We'll take the derivative of this function and set it equal to 0. We got a equals 2 pi r squared. No, 1000 over r.
That's 2000, in the answer.
2000 over r. Okie doke. So now we gotta take the derivative with respect to r. So the square goes down, so we have 4 pi r. The derivative of 200 or 2000 r to the negative 1 becomes negative 2000 r to the negative 2 minus 2000 over r squared. We took the derivative. Now we know the rate of change. We set that equal to 0. And we solve for r. So move this part over there. So we have 2000 over r squared equals 4 pi r. Whenever you have fractions and equal sign, get rid of the fractions. So multiply both sides by r squared. By r cubed. And solve for r. Divide both sides by 4 pi. So r cubed. 2000 divided by 4 is 500 over pi. And what's r? So we take the cube root of both sides. R is equal to the cube root of 500 over pi. So what happens at that R? Are we sure it's the minimum, not the maximum? How do we know if it's minimum or maximum? Mm-mm. Think of, we talked about this in chapter 3. Chapter 3, I believe, is when we graph a polynomial, we find the first derivative, set it equals 0, that tells us our vertices. How do we determine if it's a maximum or minimum? We use a second derivative to determine the concavity. If the second derivative is positive, it's concave up, which means we have a minimum. If the second derivative is negative, it's concave down, so we have a maximum. So guess what we gotta do? We gotta do the second derivative. Or we gotta take the derivative again. Oops, I'm sorry, I'm so sorry. So the derivative of 4 pi r is 4 pi. Now the derivative of this 2000 over r squared, or 2000 r to the power -2. The derivative of that becomes -4000 over r cubed. So that becomes negative, which turns out to a positive. Set that equal to 0. And solve. Actually, we'll have to solve it, we'll look at the equation. Because we're determining it, is it positive or negative? Yeah, because 4 pi is a constant, it's always positive. R can never be negative because it's a radius. So this whole function here is always going to be positive. So this is going to be always concave up. So therefore, our value that we found is a minimum. Because no matter what what we're gonna do here, we set it equals 0, we're gonna look at what the values look like. But because this is a constant term, that's a constant term, and R is always positive, so this equation here can never be negative. So it's always concave up. Which means that what we have here, since it's concave up, we have an absolute minimum. And that is going to give us the value of our lowest point, the least amount of material. So we know that at this radius, we're going to have a minimum. That's going to be least amount. So what do we plug this? We want to know what the height is. What's our formula for the height? R squared. And plug in our R. Our R is cube root of 500 over pi squared. And work it out. Ten point what? Or 10.84. Which is what we wanted to know. Because what's R going to equal? The cube root of 500 over pi. That should be something like 5.4. If you notice, the radius and the height, twice the radius equals the height. So the height is equal to 2 radius. That's going to give us the formula for our least amount of material needed. So the radius will be 5.41 centimeters, and the height will be 10.84 meters or centimeters. Because we had R here, we have plug that in there, we solve for H, we get that. That tells us our dimensions. And we know it's the minimum, it's the least amount. Why do we know that? How do we know this is going to give us the least amount of material for the one liter can? With what? Well, because well, the bottom line is because it came from our equation. You are correct, but that's it came from our equation, our formulas. The radius was just a straight derivative of our function. It gave us the maximum or minimum. And because the second derivative was always positive, we know that it's the minimum, which is what we're looking for. Remember, it's a cubic function. Why is that important? There's a cubic function looks like this. In other words, here, the second derivative is negative. And here, the second derivative is positive. Or it's possibility that can happen. But in our case, since our second derivative was always positive, we know that our function looks like this. So our radius and height are related that way. They're two to 1. Because of the values. All right, we'll pick up from here next time. How many more do we have? Yeah, the business ones come next, examples of economics. Oh, it's Wednesday, isn't it? Have a great weekend, everybody. Have a good day. Have a good weekend. Did I, did I upset you?
Me?
Yeah,
No, why?
but I thought that when we first started talking about the thing this earlier, I thought, oh, you were getting upset at me for opening my mouth and just talking.
Oh, no.
No, because I